Good afternoon, students. Could you hear me? Good afternoon, students.
Yes, sir.
Yes, fine. Okay, then we'll move on to the lecture. In the previous lecture, we have started the discussion about high performance fiber. We have discussed about one high performance fiber, which is the aramid fibers. Under aramid, we have discussed the Nomex and Kevlar, their manufacturing properties and applications we have discussed. So in today's lecture, we are moving to another high performance fiber, which is the carbon fiber, one of the very important high performance fibers. So what is this carbon fiber? Carbon is a fiber that contains at least 90% carbon in it and is obtained by the controlled pyrolysis of appropriate precursor fiber. So this is important because you see the fiber itself is a carbon that contains 90% carbon in it. And how it is obtained? You need a precursor fiber, which is a raw material, fiber. That fiber will be heated to certain temperature in different steps. That is called the pyrolysis. This is the burning. Pyrolysis is the burning. Means pyro means heat, and lysis means breaking, where that is heated to certain temperature to break into certain fragments. You produce the carbon fiber. So the precursor means it is a raw material. What is the raw material for this fiber, carbon fiber? It is the PAN. PAN is the polyacrylonitrile, which is the acrylic. Acrylic is the raw material for the manufacturing the carbon fibers. And it was first developed in 1963 in the laboratories of Royal Aircraft Establishment at UK. And this carbon fiber, it is of a great importance in the technical textile sector, especially in the composites as a reinforcement material fiber. These carbon fibers are of a great importance. So if you see the precursors, which is the raw material used for the manufacturing the carbon fibers, there are three raw materials you can be used to manufacture the carbon fiber. One is the polyacrylonitrile or the acrylic, and another is the rayon, which is the viscose rayon, and another is the pitch, which is the petroleum byproduct. But among these three, the polyacrylonitrile is the commercially very successful because of the high yield of carbon obtained from it. And it is a commercially successful precursor for manufacturing of carbon fibers. The rest through to rayon is very less it's used, and pitch is also less used when compared with the polyacrylonitrile. So what are the stages involved in the production of carbon fibers? First, you need the precursor, which is the PAN fibers, and you carry out some 3-4 steps. Like the first step is the oxidative stabilization. You can observe from this flow chart, where you heat the carbon fibers to certain temperatures, say 200 to 300 degree, and then you do the carbonization process, where you heat further to 1000 degrees centigrade, and then the next step is the graphitization, where it is heated to 3000 degrees centigrade, and then you produce the carbon fiber. Okay, so here the carbonization stage, with every stage, if you see, we are going to discuss about every stage what happens. But if you see, observe the carbonization stage, which is the intermediate stage, you can see here, where it is heated to 1000 degrees centigrade, the graphite-like structures are forming. If you observe, the carbon fiber is completely a type of a graphite structure, which is a allotrope of a carbon. I hope you may be knowing what are allotropes, different forms of carbon like diamond, graphite. These are the allotropes of carbon. So here you see the graphite-like structure forms during the carbonization, but you will not get the preferred orientation. That orientation you will get only when you do the graphitization, that we are going to see how the orientation occurs in this process. Let us start with the first step, which is the oxidative stabilization. So here what you do is you take the polyacrylonitrile fiber, and you just expose it to the oxygen environment, where you apply some high temperature between 200 to 300 degrees centigrade, so that in this temperature you allow the shrinkage to happen, so that there is no disorientation. So you heat the polyacrylonitrile. You know what is a polyacrylonitrile? It contains the C triple bond chain, which is the nitrile groups, polar groups are there. So that what will happen? these polar nitrile groups will start burning, so that what will happen if you burn it, it will start breaking down into fragments. Okay? So here, if you observe what is present in the structure, just I will show you here. This is the first step, where you can see this is the C triple bond N. Once if you start burning to 200 to 300 degrees centigrade, two things you can see. One is the cyclization, another is the dehydrogenation, where you can see dehydrogenation means where the removal of hydrogen, where the hydrogen gets removed, and one by one the parts start breaking it actually into various type of fragments. Here you can see this cyclization, where both cyclization and dehydrogenation take place simultaneously. It take place, so that what happens, the hydrogen present in the structure that gets separated out. And if you observe in the more, for a more clear understanding, you see the interior. This is the structure of the polyacrylonitrile. You can see here. Here if you see here, you can see this hydrogen which is present here. This will get removed. Okay, this is the dehydrogenation reaction that take place during the oxidative stabilization. One by one, all the elements finally, the whatever you're heating it to high temperature, finally you need only the carbon. You want the rest of the elements or atoms to get removed, like a hydrogen, nitrogen, to get removed. Okay, so that is what I showed this. I want to show this here. So this hydrogenated naphthyl pyridine rings, whichever that increases the thermal stability of the polymer, so that you are heating it to high temperature, so that will get broken down and hydrogen gets removed. Because you know very well, hydrogen is a highly flammable material. Okay, so if once that is removed, so then the next step is the carbonization. Here, what you do is you heat it to further high temperature, where carbonization, where you are heating it to high temperature around say 1000 degrees centigrade, and in this process also some low molecular weight gaseous products like hydrogen cyanide, ammonia, hydrogen, carbon monoxide, carbon dioxide, all these low molecular weight compounds are removed from the PAN fibers, which has already undergone oxidative stabilization, so that you will get around 50% yield of the carbon fibers in this stage itself, so that whatever volatiles that are produced, that is a low molecular weight compounds, that will get removed at 1000 degrees centigrade. So that at this stage, if you observe, what will be present is mostly carbon and some nitrogen atoms in aromatic ring in some parallel planes. I will just show you the figure. But one thing you need to understand this, even at this step, you will not have a proper oriented structure. And whatever fiber that is produced, that will have a low tensile modulus. I will just show you a small diagram. What happens here? You see here the dehydrogenation occurs, where the hydrogen gets removed, so that only here you can see only the nitrogen. And in the next step, when you heat it above 1000 degrees centigrade, what happens? The denitrogenation occurs, where most of the nitrogen gets removed. You can see here the nitrogen that is present here at the side, that gets removed, so that these fuse together. Only a less number of nitrogen atoms are present after the carbonization process. Okay, so if you observe here how the every products, how it is removed, you can see here how the water, it gets separated out, so that the ring fusion take place, so that once the water gets separated out, so the benzene rings which are present here, they fuse together. Okay, so here also you can understand once this nitrogen which is present here, when this gets removed, the structure gets fused. There is some cross-linking take place. That is why you get a higher carbon yield. Around in this process itself, you get 50% carbon from this process, but still there is some disadvantage, because the structure is not ordered and some nitrogen atoms are still left in it, and the filaments whichever is produced, that has a low tensile modulus. Okay. So next is the graphitization process, which is the final process in the carbon manufacture. Here, what happens is you heat it to still higher temperature, double, triple temperature of the oxidative stabilization. Once, if you just recall the flowchart, you can see here, if this is 1000-degree carbonization, if it is 1000-degree graphitization, you apply at least 2000 to 3000 degrees centigrade. You apply, so that in this process, what happens? The structure becomes more ordered. Okay, so that what will happen? The carbon fibers will form an ordered structure. Okay, that ordering is very important. Then only you will get the good mechanical properties like the higher tensile modulus uh, and also tensile strength you will get. And in this process, one important thing is you need to apply some tension, some stretching you need to apply. Okay, though there is a good high temperature itself that can remove the low molecular weight fragments and becomes more ordered, still you need to apply some stretch so that you allow the graphite structure in the form of a proper alignment. Okay, so that you apply certain percentage of stretch, around say 30% stretch you are applying, and you will get a moduli of say 700 gigapascal you will get. So that you need to apply some stretch during the manufacture so that the graphitic planes get aligned in the filament direction. Okay, because you know well that orientation is very important for the mechanical properties. Okay, so this is important step. If you just see the process here, this is how it works. The pan fibers or the raw materials are passed through the oxidizing atmosphere, which is a temperature of say 200 to 300 degrees centigrade. It undergoes oxidative stabilization, and the next step, it is performed in an inert atmosphere where the low molecular weight fragments like hydrogen cyanide, carbon monoxide, carbon dioxide, hydrogen and nitrogen, whichever is low molecular weight gaseous products are there, those gets removed. Okay, but still there is some nitrogen left out, and structure has not become realized the actual graphitic form. So for that, you still expose it to very high temperature, where along with the temperature you give some stretching so that at a very high temperature of say 2000 to 3000 degrees centigrade, you will get the graphite structure. Okay, that is the culmination where the carbon fiber yield is achieved with the proper orientation is obtained, so that you produce a carbon fiber. Okay, so this is for the pan fibers. Pan is a polyacrylonitrile, which is the acrylic. But there is another precursor also, which is called the pitch, that we'll see now. So pitch, you know what is meant by pitch. You may have heard this word from your school chemistry, which is a byproduct of petroleum obtained by the coal coking or refining. So here, what you do is the carbon atoms, they are arranged in the low molecular weight aromatic ring patterns. So here, this pitch, you will heat it to certain temperatures like 350 degrees centigrade, and so that what will happen, you will get some two-dimensional structures you will get, which is actually in the form of a liquid crystal. Just if you recall the aramid fibers that we discussed, it will have both the solid nature and as well as the liquid nature. In between that, it will form a liquid crystal type of a domain it will form, so that once that liquid crystal, or you can say it is a mesophase, which is in between the solid and the liquid, that can be spun through the melt spinning system, so that the molecules get aligned, and so that you will get some strength, and the orientation can be obtained, and a green yarn can be produced. So there is a green color type of a fiber can be produced. Okay, so that once the yarn is produced, you can do the after treatments, like you can cool it and subject it to some softening temperature of say 250 to 400 degrees centigrade, so that you can in the oxygen atmosphere, this to avoid the fusing of the filaments, you can perform this after treatments, and then you can do the carbonization. Okay, in this carbonization, you can perform the carbonization without any kind of a stretching or anything, so that this is an advantage where without applying any kind of a tension or a stretching, you will be able to develop the molecular orientation for the obtaining the required modulus and high strength. Okay, so this is an advantage when compared with the rayon or pan process. In rayon or pan process, we apply tension and apply stretching. Here we do not do it. We just directly do the carbonization and we obtain it. Okay, then for example, if you do the next step like graphitization, where orientation, the graphitic type of a plane that you can obtain from the graphitization, the final step you can perform. So that here, if you observe, during the uh, heating first stage, during the oxidative stabilization stage itself, we have converted the pitch into the mesophase pitch, where it has a liquid crystal nature, so that because of the liquid crystal nature, here the orientation is achieved in the spinning process, which is the melt spinning process, where without any kind of a tension, the molecules will get arranged and you will get a lamellar type of a structure, like a uniform model you will get, like this, which you can see in this diagram. So that is the advantage here in this. By using the pitch, you can eliminate the tension or stretching, so that by doing the spinning process and because of the maintenance of the liquid crystal nature of the uh, solution, you can manufacture the fiber with good mechanical properties like orientation and tensile modulus and tensile strength. And now we will see the properties of carbon fiber. If you observe, we have not discussed about rayon fiber. See the raw material, how we'll decide the raw material. Any kind of an organic compound, if you burn, it is finally going to produce a carbon. Okay, but we choose the raw material based on how much percentage of yield of carbon we will obtain. That is why we always prefer the polyacrylonitrile fibers. Okay, so if you see the commercially practiced process is the polyacrylonitrile process. When compared with the pitch, is actually used less when compared to the polyacrylonitrile. Okay, so now we'll move on to the properties of carbon fibers. So if you observe the carbon fibers, the color is black in color and have a smooth surface and a silky luster is there. They have a round cross section with the flattened sides. If the fine structure of carbon, it is similar to the graphite, which is a pure carbon, but here it is not a pure carbon. It is only 90% carbon. They are arranged in the form of a hexagonal arrays of atoms, producing a crystalline structure. Because of the close packing of the structure, if you observe, all the carbon hexagonal benzene rings are fused together, so it has a good strength and modulus. High stiffness will be there, so the fiber is strong. And these fibers can be classified on the basis of a high strength, high modulus, and ultra high modulus fiber. The tenacity is very high, around say 11 to 24 grams per denier, and elongation at break is around 0.5 to 1.5%. And the specific gravity is high, 1.77 to 1.96. So it is a second heaviest textile fiber, you can see. If you see observe the specific gravity. And this fiber, it is mostly made up of benzene rings, so it has a 0% moisture regain, because all the water loving groups are eliminated by this heating process, so there is a 0% moisture regain. And if you see, compare this high strength, high modulus and ultra high modulus fibers and single crystal graphite fibers, you can see wherever the carbon yield is very high, that will have the different properties, and wherever the carbon yield is little low, there will be a change in the properties. If you observe here, this both high modulus and ultra high modulus, these have a very high carbon component, so obviously the density will be higher. And denier also, if you observe, denier will be higher. Modulus, if you see ultra high modulus, you can observe in both these cases the carbon component is high, so the modulus will be higher. And since the modulus is very higher, there is a extension there is an elongation to break that will actually reduce, that is 0.62, because it's a very stiff material. Tensile strength, also if you see, it is completely packed, so that tensile strength will slightly reduce, around 2.2 to 2.4%. And this is very important, electrical resistivity, that we are going to see this electrical resistivity, which is expressed in ohm centimeter, because these fibers are very good conductors. Okay, so this if you observe the normal carbon fiber, which is around 92 to 94% carbon component, they have a high resistivity. Okay, so resistivity, it is opposite to the conductivity. So that you can say, when the modulus goes on, we increasing the higher modulus where the carbon component is very high. In that case, the conductivity increases, because conductivity, it is a reciprocal of resistivity. Okay. And if you see the other physical properties, the density, we have already seen the specific gravity, it is very high. The density, if you see, it is around 1.7 to 2.2 grams per centimeter cube. And it is obtained based on the precursors. If you manufacture the carbon with the pan fibers, then it may be different from the carbon that is manufactured from the um, rayon or pitch. So it depends upon the processing conditions, precursor type, and the heat temperature. So this modulus, if you see, the higher modulus is the cost of toughness. So more carbon component, if it is present, then it will obviously have a higher modulus. And the modulus, it is actually based orientation dependent also, how the process condition you have aligned in the fiber axis, the degree of the order and the temperature, these things matter actually in the modulus. But if the fiber, if in the pan based fibers, if you observe, the order is more over order, so that you will get a good strength and the mechanical properties. But if there is more modulus, then in that case the elongation to break actually gets reduces significantly. That is to be understood. That is what is shown here. If you observe the modulus, if it goes on increasing, this becomes more stiffer, so that it can easily, if you just extend it, the tensile elongation will be less. Okay. And if you see the pitch based fibers, they have a high modulus. And you see the important point to be noted in the carbon fibers is they are electrical conductors. So it is used as a conducting material in the technical textile application. But there is some disadvantage also, that it may create some short circuiting also if it is not done proper earthing, or anything is not done properly. So that is to be taken care, but these are very rare kind of a problems. So these carbon fibers, there is some advantage and disadvantage also that we will see. If you observe this carbon fiber, like all the textile fibers or the polymeric fiber, this is a highly anisotropic fiber that will have different properties in different direction. But if you see in the carbon fiber, this is more prevalent, where if you see in the in plane, that is in the in plane property, it will have a different property when compared to the out of plane, that is perpendicular to it. If I just draw a small diagram for you to explain. See, for example, this is the carbon fiber. So here, if you see this, this is the across the plane, and this is the along the plane. Okay, so carbon fibers will have certain property. This side, the property will be different from the property this side. This is the across the plane, this is the along the plane. So what is the difference? If you see, the in-plane properties will be very different from the properties perpendicular to the plane. So if you see, the coefficient of thermal expansion means, after applying the temperature to a particular material, how much it expands. That actually varies in the carbon, because carbon has a different property in plane and different property across the plane. So if you see this carbon fiber coefficient of thermal expansion, it is 7 into 10 power minus 6 and 12 into 10 power minus 6 in a perpendicular direction, but whereas it is minus 0.5 to 10 power minus 6 and minus 1.2 to 10 power minus 6 per Kelvin in the fiber axis direction. So there is you can see how much difference is there. So this is the difference because of the different properties in the in plane and across the plane direction. Okay, that is why if you see, modulus is also different in the in plane direction and the out of plane, that is the across the plane direction. If you see in the perpendicular direction, it has a 12 to 20 gigapascal, but whereas in the axial modulus, which is along the plane, that has the 250 to 390 gigapixel. This actually makes the carbon fibers a different fiber when compared with the other commodity fibers and high performance fiber. It is a highly anisotropic fiber when compared with the other fibers. Okay, so there are some problems associated with that also. That is why we do not use the carbon fibers alone. We use it for manufacturing the composites that we will see now. Now we will see the chemical properties. Chemical properties, if you observe, it contains mainly carbon, so it will be resistant to acid and alkali. It has a good chemical resistance. But if you use a strong oxidizing agents, then it will degrade the fiber, and they are inert to all solvents except the hypochlorite, but sensitive to hypochlorite because hypochlorite is a strong oxidizing agent, and they have excellent resistance to biological organisms, aging, and sunlight because in the structure mainly the carbon is there. So it is carbon is actually resistant to these microbiological organisms, aging, and sunlight exposure. And these fibers do not melt; they oxidize slowly at above 300 degree centigrade. Application, yes, application, it is a very diverse and important applications are there in the technical textile sector, mainly for the industrial purposes. So it is not used alone because the fiber, as I've already told you, it is a highly anisotropic fiber. The in-plane direction property and the across the plane direction property, both are different. So that is why what we do is we use this as a reinforcing material in the manufacturing of composites. Okay, so that is, if you see here in the second point, it's mentioned you can actually take a binder, you can take a matrix material, which is a type of a resin, like a epoxy or any kind of a resin you can take, and then you can combine this with the carbon fiber to make a composite. Okay, so that what will happen, this carbon fiber different properties problem whichever is there, like coefficient of thermal expansion, that can be taken care of. Okay, so that is the reason why this carbon fiber biggest application in the composites. Okay, especially in the aircraft where the people are flying, so that aircraft parts are made up of carbon fibers, carbon fiber composites. Space vehicles, where the people are traveling in the space, those vehicles are made up of a composite, carbon reinforced composites. And other application, there are other properties are there because of the high specific strength. In particular direction, it has a high specific strength, and stiffness in the particular direction is very high. So it has a good temperature resistance, this electrical conductivity, chemical and biological inertness, electrical conductivity, very important property. It is used as a very good conducting material. Then good vibration damping ability. See, to vibration damping means wherever there is a sound generation, the vibration is there. That places, it can be used as a vibration damper so that excessive vibrations can be prevented. For example, in the cycle, it can be used as a good shock absorbing vibration arresters. Okay, and it has a good fatigue resistance also. If you give any kind of a wear and tear or any kind of a process it undergoes, it will not easily get fatigue. Okay, it has a good fatigue resistance that is useful in certain application. And as I have already told you, it is used in the space vehicles where it can be used for manufacturing the rocket casings also, where the rocket is placed in a particular box. Okay, those box is made up of a carbon reinforced composites. And cargo bay doors, which is in the space vehicles, this space vehicle application is also there. And modern fighter and commercial aircraft, they have a number of application: turbines, compressor, helicopter blades, windmill blades, flywheels, moving parts, and shuttles. In textile machinery, these are made up of a carbon fibers. If you see in medical textile also, it has application like a ligament and hip joint replacement, heart valves, and surgical implants. Whether you need to implant some material inside the body, this carbon fibers can be used. And sports application like racing car components, tennis racket handles, pole vaulting poles, rowing oars, where in the ship where they use this small wood material for rowing it to move the boat. These oars can be made up of a carbon. Tennis rackets, you may have seen the tennis racket, those are made up of carbon. And the racing car components, handles, and pole vaulting pole, where there will be a small stick, a big stick, where the people will be using to just jump around. These vaulting poles are made up of carbon. So there are diverse applications are there. If you see the demerits of the carbon fiber, there is some demerits also. One is that it has a low impact strength. Okay, why there is a low impact strength? Because the properties in the in plane and across the plane direction both are different. So if any kind of a material is coming and hitting on that carbon fiber material, it will lead to the damage. Okay, and another problem is they are expensive. Okay, so the reason for the impact strength I have told you, because in the perpendicular direction and the in-plane direction, the properties are different, and it has a low extensibility also. So that is why you see, for example, if a carbon fiber, it is used alone in the aeroplane wing. For example, if in any aeroplane wing, it is manufactured with only carbon fiber. In that case, what will happen if any kind of a bird, if it is just flying over the uh, sky, if it is trying to hit the aircraft, what will happen? That will lead to breakage because of the high impact force that has hit the blade. So because the properties of the blade in both the axial direction and the other direction both are different, so that is the reason why the carbon fibers are seldom used alone. It is used for as a composite. It will be mixed with a matrix material like an epoxy or a vinyl ester or any kind of a chemical based matrix is taken, and carbon fiber is taken. Both are mixed together to make a composite. Okay, so that these shortcomings can be overcome. Okay, so that's all about the carbon fibers. In this lecture, we have seen the introduction to carbon fibers, what are carbon fibers, what are the precursor used carbon fibers, and we have discussed about the pan fibers, which is the commercially used raw material, how it is manufactured, oxidative stabilization, carbonization, graphitization steps we have seen in how each step is different and how it leads to the perfect carbon ordered fiber. And then we have seen the pitch-based precursor, where we manufacture the carbon fiber through the pitch, which is a byproduct of petroleum. And then we have seen the properties and the physical and the chemical properties and applications we have discussed, and the demerits also we have seen. And with this, the carbon fiber discussion is completed. It's a very interesting and easy to understand fiber. So that's all about the carbon fibers. If you have any doubts, you can ask.